Welcome to SSR Meetup. This is the second part of the DID marathon that we have today with Drummond Reed and Markus Sabadello. Like 60 minutes ago, we had a DID working group update about the face-to-face meeting they had in the Netherlands. And this is a follow-up on an almost completely different subject because Drummond and Markus, they are the co-authors of the DID chapter. Like, I mean, there's just one chapter that they co-authored in the book, but they will be they are co-authoring many more chapters. But what we have decided that as part of the work that we do at SSI Meetup is that we will be sharing the deep insights that we have been developing in that book that will be coming out this summer. You have this already available in MEEP, which is the Manning Early Access Program, and we will share a link at the end of this presentation, or just check out the IdentityBook HQ Twitter account where you will have a link too. And chapter 6 concretely is the DID chapter. So the DID chapter is an amazing chapter that Drummond and Markus have written, which I have been really impressed with, and I think it's the best that has ever been written about DIDs, and also the other chapters. But we wanted to start with this one. We will be bringing out many more specific IdentityBook.info special webinars, and this one, well, I think we all have the privilege to hear from Drummond and Markus about what they're working on and really understand the baseline, and this will help you to understand webinars like the previous one we had about the DID working group, where once you understand the basics of how all the stuff is constructed, it will also help you to understand how it's being developed and how to create real SSI decentralized solutions. Quick follow-up on SSI Meetup, what we're trying to do here. This is open to everyone, companies, individuals, associations. What we hope and desire is that you use this material around the world. We know this is happening already. People are using it all over the place in Asia, America, Europe, South America, so we're really happy with that. It's a Creative Commons by share alike license, which means that you can reuse this material, and you just need to give credit back to the authors, which today is Drummond and Markus and SSI Meetup, and then you can reuse it. If you have any questions during this presentation, which will be an amazing deep dive presentation, please pay attention, take notes, ask the questions that you have, because this stuff is really, really interesting. Yeah, and that's about it. Drummond and Markus, thank you so much for being with us today here again. This is the landing page of the book that I was talking about before. You can get the self-sovereign identity book already. You can have chapters 1, 2, 3, 4, and chapters 5, 6, 7, which is architecture, cryptography, verifiable credentials, and DIDs. The verifiable credentials chapter has been done by David Chadwick and Dan Burnett, and then the many other key people that we will be inviting and showing up here at SSI Meetup. Drummond and Markus, please take it forward from here, and I'll be bringing up questions as they come in.
Excellent. Thank you again, Alex. It's good to be back for part 2 of our DID marathon today. And so what Markus and I are going to do is walk you through the content of this chapter. It is one of the longest chapters in the book because we decided, hey, if we're going to write a full treatment of DIDs, we're going to go all the way down. And we actually begin the chapter with this diagram because as two people who have been involved with DIDs for a very long time, we find that there really are these 4 levels, progressively deeper and deeper levels of understanding DIDs. And today we're going to actually do the same thing we do in the chapter. We're going to work our way down through all 4 levels. The deeper it goes, the heavier it gets, but hopefully the more insights there are. We won't spend a huge amount of time at the bottom level, just a couple things there, but we'll work our way down through that. And we'll each sort of cover the parts of the chapter that we contributed most to, and then we'll provide commentary throughout. So let's start with the superficial level. What is a DID? And the really short answer about it's technically a URI that, as you see in this diagram here, the URI space is very broadly divided into URLs, uniform resource locators, and URNs, uniform resource names. And the difference between those two, way back at the start of the web architecture, was a URL points to something that exists on the network, and you can go locate it and retrieve the resource. Best example being every time you click a link on your browser, you get back a web page. That's the resource you're getting back. Whereas a URN, and by the way, those resources can change. They can move. They can, they're not. There's no requirement that they be persistent. Whereas a URN is exactly the opposite. It's an identifier for something that is designed to never need to change. And by never, we mean like ever. It's supposed to be a globally unique identifier for all time for that resource. And that if a URN does resolve, it typically goes through a process resolving it to one or more URLs that will point to instances of that resource someplace on a network. But URNs don't necessarily resolve at all. They just are persistent identifiers for things. And so the interesting thing about a DID is it's functionally equivalent to URN. It's a persistent identifier for something. But the resolution process can result in one or more URLs that do point to ways to interact with that resource on on the web, on the network. And so it combines sort of, some aspects of both of them, and then adds some others we'll cover in a minute. Markus, anything else you want to say about this, the overall structure of DIDs?
Yeah, I would just say that the main thing to keep in mind here, or to learn from here, is that the DIDs are completely in line with web architecture, right? DIDs are a kind of URI, and typically when we think about the web, we think of HTTP URLs that we type into the browser, but the web is not limited to a certain type of URI, so you can just as well imagine a web that's built on top of this new type of identifier, the DIDs. Actually, there's an interesting quote from Tim Berners-Lee. I think he said the DNS is the Achilles heel of the web. So you could imagine a better web that's built on this new type of identifier. And the other comment, this is the SSI book, right? And there are lots of chapters about many different components and technologies for SSI agents and wallets and verifiable credentials. But really, the essence or the origin of an SSI system is identifiers. That's the core building block. That's how that's where you start when you build SSI. If you don't have identifiers, then you cannot have relationships. You always need names and numbers and addresses to refer to one another and to build connections and to exchange data and messages. So and that's why the DID community or the SSI community came up with this idea that we need a new type of identifier if we wanted to build a new type of identity system.
Exactly. And that new identifier, if you've attended any of our webinars before, you've seen this set of the 4 core properties of a DID. This has been, I think it was enumerated in the very first version of the spec, and it hasn't changed. And again, there are identifiers out there that provide some subset of these properties today. Persistent identifiers, for instance, URNs. There are many forms of URNs. All HTTP URLs and domain names and everything are resolvable. There are what are often called CIDs, cryptographically verifiable identifiers where you can prove that it is the identifier for a resource. Content based addressing is one of the best known examples of that. It's used by IPFS and other systems. And there are even decentralized identifiers. Probably the best known is UUIDs, universally unique identifiers, that are produced following one of several algorithms. There's a whole Wikipedia page on it. So that they're basically all but guaranteed to be universally unique based on the randomness or the algorithm they used to generate it. And they've been in use in distributed systems for several decades now. What a DID does is combine all four of these properties, right? It's persistent. You can resolve it into this thing we call DID document. We'll talk about DID resolution in a minute. They are cryptographically verifiable in many different ways. That's every DID method can define how that happens for it. And they are decentralized. They do not require centralized registration authorities. So when you combine those four properties, you get this new identifier, which, as Markus pointed out, it's the first new identifier that I believe the W3C has undertaken since it started with HTTP and HTTPS identifiers, you know, in its history. So that's why we're here, an identifier that does these four things. Any other comments on that, Markus, before we dive down to the next level?
No, not here. Those are the four main properties. Yeah. Great.
Okay. So we're now going to go down to the next level and how DIDs work. And Markus did the majority of the work on this chapter, so I'm going to click in, and we'll start with this quote right out of the book here. I like this, you know, the whole sense of identifiers. It's not the identifier itself, it's how it's used and the particular type. And keep this in mind, we'll come back down to this at the very lowest level when we talk about the semantic meaning of DIDs. But let's dive into, okay, what is the usefulness of this? So take it away, Markus.
Right, so the quote on the previous slide basically says that there are some rare scenarios perhaps where identifiers are useful just by themselves, just as addresses, names or numbers, but in almost all cases an identifier is used for something. You use it to start some interaction or some kind of protocols. In other words, you resolve it, right? That was one of the four core properties. That's the nature of URLs on the web. If you have that identifier, you can access it somehow. You can interact with it, and the main function of DIDs is that you can, when you resolve a DID, you end up with not with a web page or a picture or a PDF document. That's what you usually do with HTTP URLs when you type them into a browser. But with a DID, when you resolve it, not really with a web browser, but using some other kind of DID-enabled application or service, you can resolve it to this data structure that's called the DID document. And that DID document contains basic data that is needed in order to interact with the subject, to then trigger some kind of interaction, some kind of protocol to exchange verifiable credentials or to create connections or exchange some other kinds of messages. So that's the basic piece of information, the DID document, that can be looked up, that can be resolved from the DID. And there's in this diagram you can see something like a triangle between the DID on top, the DID document on the left that the DID resolves to, and the DID document on the left describes the DID subject. And the DID subject then at the same time is what's being identified or denoted by the DID. In this diagram, it's a person, right? It's not necessarily always a person. It can be an organization or a thing or an animal or anything else. And this again is very much in line with web architecture itself. So on the web, we sometimes say there are information resources. Those are things on the web that have URLs that you can dereference, that you can access. That's what the DID document is. It's an information resource. But the DID subject, that's so-called non-information resource, that's what the DID identifies. It could be me, it could be Drummond, it could be the SSI meetup organization. And this triangle between the identifier, the DID document, and the DID subject, that's really the core functionality that DIDs provide, and that everything else builds on top of.
Before we leave this diagram, there is one important point. Markus illustrated this diagram from the book, that this DID subject is controlling, obviously, the DID and the DID document. Now, in the DID specification, we call out that role separately as the DID controller, because as soon as you turn around and say, oh, it's not a person here, it is, you know, an organization, a thing, a product, an animal, obviously it can't be the controller of these things. It is the subject of the DID. It's identified by the DID, and the DID document describes it, but the DID controller would be another party. And so we call these two scenarios. This is the DID controller equals DID subject, is what you're seeing in this diagram. But we also have the scenario where the DID controller is not the DID subject. And we'll talk more about that as we get deeper into the whole thing. But I just wanted to point out that it's not always the case that the DID subject is a controller. All right, on to DID documents.
Okay, so again, the DID document is the information resource on the web that the DID resolves to, and the intention is to enable interaction or connections with the DID subject. Now, in theory, the DID document could contain any arbitrary information to describe the DID subject. It could even contain personal data such as a name or an email address. Most of the time, we try to discourage that, especially for DIDs that identify people, for privacy reasons, because the DID document is essentially public. Anyone can look it up, just like if you have a domain name, anyone can resolve it to an IP address, and that's public information. So most of the time, we're saying that a DID document should only contain the minimum amount of information that's needed in order to then bootstrap some other kind of interaction, some protocol, agent-to-agent protocol, or exchange of verifiable credentials. There are other chapters in the SSI book that go into more detail on how that exactly works. But the purpose of the DID document is essentially to bootstrap these higher level interactions. And so most of the time in a DID document, you will find it's essentially two things. You will find one or more public keys that are associated with the DID subject, that are under the control of the DID controller, which again is sometimes the same as the DID subject, and sometimes it is not. And you will find service endpoints in the DID document, and those tell you how exactly you can interact with the DID subject, what kind of protocols, what kind of network endpoints are available to connect, for example, to an agent that represents the DID subject, so that you can then exchange credentials or some other messages. The document may contain some additional things like timestamps or information related to delegation, authorization. There are different architectures, different applications that use the DID document in different ways, but essentially most of the time it's the keys and the service endpoints. Drummond will talk quite a bit more about the public keys and how the keys relate to the subject, but let me just make one note here that this is really the essence of self-sovereign identity and how it's different from other identity systems. The fact that a DID is independent of a central authority. A DID is created and managed by the DID controller alone, and it has associated cryptographic key material. So from a, I don't know, philosophical point of view, you could say in an SSI system that's based on DIDs, the act through which a digital identity is created happens without any intermediary, without any central authority, right? I don't have to register username and password in somebody else's database. I don't have to get an identifier registered in a centralized or hierarchical system. All I have to do is create cryptographic key material and create a deed, and the public key is associated with my deed and in the deed document. That's really the core building block I think of what enables SSI. Here's
go ahead.
Here's just a quick example. The typical deed document, it contains one public key, which is it says here it's used for authentication, so that public key can be used by a client or during some interaction with the deed subject to prove control, so that the deed subject can be authenticated by the key that's in the deed document. And then there's the second entry here is a service endpoint. In this case, it says verifiable credential service, but it could be any protocol really that's available for communicating with the subject. Could be a social networking protocol, could be an identity agent, could be some personal data store protocol. But this is very typical pattern that we have these two things in the document. And then, so this is very important. So there's no single technology, there's no single registry for deeds where deeds are registered, and there's also not a single decentralized system like a blockchain or distributed ledger that all deeds use. In fact, you could think of the deed of something like a framework or a concept that can be implemented in different ways, and those different ways of implementing deeds are called deed methods. So a deed could be created and managed and resolved using a blockchain like Bitcoin or Ethereum, but there are also other types of deeds, and there are different distributed ledgers. So there are, and we'll have another slide a bit later about different types of deeds, but it's important to know that there's not one database or not one blockchains where all deeds are registered, but there are all these different methods, and the individual deed methods specify how exactly a deed is created and updated and resolved and also deactivated within a particular system. And as long as a deed method fulfills some basic requirements which are outlined in the W3C deed specification, so there's a list of requirements for deed methods, but as long as these requirements are fulfilled and the 4 core properties that we talked about, then you can have a deed method, right? If the identifiers are persistent and resolvable and cryptographically verifiable and decentralized, and they can be, and they support the basic operations like creation and resolution, then there are different so-called deed methods that enable this. And here are just some examples, but by now I think we have an informal registry of about 40 different deed methods. Here are just some examples. One thing you can see here is that the syntax, it always starts with deed colon, right? This is a basic syntax that all URIs, all types of URIs share, not just deeds, but all URIs start with the scheme identifier and a column. That's the deed. Then we have this method name. Again, that defines how exactly the deed works, how it is created and resolved. And after that comes what we call the method specific identifier. And as you can see in these examples, that can be very different depending on what the deed method is. So the appropriate deed method will specify the syntax and the functionality of this specific type of deed. And sometimes this is in the case of some of the Ethereum-based deeds, these are addresses of smart contracts. Ethereum, but in some other cases, the identifier is a hash of a public key, or an identifier of a specific transaction, or a random number. It could be different for each method, as long as the core properties and the core functions can be provided by the DID method. And okay, DID resolution. So we talked about that already. Is one of the 4 properties of DIDs that you can resolve them to a DID document. That's what URLs essentially mean, to be able to resolve the identifier, in this case, to a DID document. Again, one thing that's always important to mention here is that DID resolution is not a single protocol, right? So if you think about DNS resolution, then that's a very specific, concrete client-server protocol. If you want to resolve a domain name to an IP address, then you have a DNS client which talks to a DNS server, and then it just executes that standard protocol to resolve a domain name. DID resolution is different precisely because we have all these different DID methods. So it's more helpful to think of DID resolution as an abstract function or an algorithm with certain inputs and outputs. The input is the DID plus some optional parameters, and the output is the DID document. And again, how exactly that works under the hood, that depends on the DID method. There are even DID methods where resolution doesn't require any network interaction at all, and then there are DID methods where resolution requires communication with a blockchain. But the DID resolution is essentially an abstraction layer on top of these different DID methods. What you see in the sorry, can I go back just one second? Sure. What you see in this diagram is just one example scenario where DID resolution is needed. In the book, there are actually several more diagrams, and we envision that there will be many use cases where DID resolution will just happen automatically, or in a way that end users will never notice. It will just be a very ubiquitous function in SSI systems, just like today DNS resolution happens all the time. It's just in this diagram, that's the specific example where a verifier wants to check the integrity of a verifiable credential. So you can see a very basic example of a verifiable credential, which consists of an issuer, then claims about a subject, and then a proof. And so when a verifier receives this and they want to check the integrity, they want to check that it was indeed issued by the trusted issuer, then that's where DID resolution would happen, because you know who the issuer is, but in order to verify the proof, to verify that the credential is correct and has not been tampered with, you need to find out what's the public key of the issuer, and that's what you do with resolution. So you look up, you resolve the issue DID, you get the DID document, you find the public key, and then you can verify the integrity of the DID document. But again, this is just one example out of many where DID resolution will happen. Other examples include authentication protocols, such as DID-auth as an umbrella term for many DID-based authentication protocols that are under development. So again, we think it will be a very ubiquitous function in SSI systems where DIDs will essentially be resolved all the time. Okay, going to this slide. So this takes us back a little bit to fundamental web architecture, where remember we said that DIDs are a type of URI. They're a little bit like URNs also, because they're persistent. They're also URLs because they can be resolved and dereferenced. But here's something else that we can do, we can add some of the familiar syntactical URL components that we know from HTTP-based web addresses, and we can also use them together with DIDs, and by that I mean the path and the query and the fragment, right? When we access resources on the web today with web browsers, and we navigate through web pages and so on, then we're not just working with domain names, right? We're not just using domain names, but we're using these HTTP URLs, which start, or which in the beginning they have a domain name, but then they can also have path and the query and the fragment component to identify other resources under the authority that's represented by the domain name. And in the DID specification, we have an equivalent mechanism or pattern, which we call DID URLs, and DID URLs are essentially the DID plus other components like the path and the query and the fragment. So a DID is not just an identifier by itself, but it can also be the root for an entire namespace or identifier space to identify anything underneath the DID itself. In this example, you actually also see another syntactical component in the middle, where you see there's a semicolon. So this is something that we don't have typically in the traditional HTTP based URLs, but it's an additional syntactical component called the DID parameter or matrix parameter that we think is useful, especially in conjunction with DIDs, and that's a mechanism essentially to pass parameters as part of the URL that influence the resolution mechanism, or that gives you more control over how DIDs are resolved and how DID URLs are dereferenced. And here are some more examples. Again, we think there will be many uses for DID URLs, just like, and we cannot predict all of them, right? So the DID specification will not actually specify what kinds of identifiers we will see in the future, what kind of path or query or fragment components we will have in the DID URLs. That will be up to application and service developers, just like the HTTP specification does not tell you what to do with those URLs. Maybe just to go over some of the examples, or try to understand what they mean. The first example is just the DID with a slash, so that's a DID URL that identifies the DID document itself. That's very simple. And the second one is interesting. That one is the DID with a fragment. So the fragment should be quite familiar also from HTTP and traditional web, where the fragment identifier is used to point to a specific part of a web page, right? If you click on an HTTP link with a fragment, then it will jump to a specific point in that web page, and we can use a similar mechanism to identify a specific part of a DID document. So if we want to create applications or services that don't just need to know the DID by itself, but they need to reference a specific key inside the DID document, then they can use this fragment syntax. Maybe just quickly the third example. That's here again. There's the semicolon syntax. That's one of these DID parameters or matrix parameters. There will also be different ones, and here's just one example that would give you some control over how the DID is resolved, and in this case it indicates a specific version of a deed document. So deed documents can be updated. They can change over time, and sometimes it may be helpful to have an identifier for an earlier version of the deed document if you don't want to know what are the current services or the current public keys associated with the deed, but you want to reference the keys associated with the deed at a particular point in time. And that's also something you can do with this deed URL syntax. And again, we think in the future that we will find many more patterns for this kind of very flexible identification mechanism. Okay, so in the book chapter, of course, we also thought quite a bit about how deeds relate to other kinds of identifiers. We already talked a little bit about domain names and DNS and so on. So we have an explicit comparison in the chapter of how deeds relate to domain names. There are some similarities. They are both globally unique. They are both resolvable, but there are also many differences, right? So deeds are by design persistent, whereas domain names are reassignable, right? If I don't pay for my domain name, or if I get to renew it, then it may be reassigned to someone else and used for other applications or other identification. They're both resolvable, but the resolution works differently. Like we said, domain names, they have a standard client-server protocol, whereas with deeds, resolution is dependent on the deed method. And of course, the most important difference, kind of the last 3 rows in this table, deeds are completely decentralized. They are cryptographically verifiable, so they have these properties that we need for self-sovereign identity. They are not dependent on a central or hierarchical registry, and no one can really take a deed away from me, whereas a domain name can theoretically be deleted or manipulated. And so we also mentioned URNs as a class or a subtype of URIs in the beginning. URNs that are persistent, and deeds are certainly not the first type of identifier that provides this property of being persistent, of not changing. In fact, there are entire communities. There's even a dedicated conference that deals just with persistent identifiers and different types. And here's a diagram of some of these types of persistent identifiers. And one thing to point out here is deeds are the only ones that are completely decentralized and cryptographically verifiable. All the other ones that are in, well, that's not true, not all the other ones, but most of the other ones depend on some kind of registry authority, some kind of hierarchical or centralized mechanism where they are governed and registered. The ones on this diagram, at least, the ones that are really fully decentralized and don't need a central registry are deeds, and then UUIDs and nicknames on the bottom, but those are not resolvable, right? So deeds are really the only ones that are resolvable and decentralized and persistent and cryptographically verifiable. And then, so we mentioned before the concept of deed methods, that there's not just one type of deed, not just one mechanism for creating and resolving deeds, but we have all these different mechanisms, different deed methods. Again, I think about 40 known ones by now. Of course, anyone can create a new deed method. We just need to write a specification, and over time we observed that there are some common patterns or some common shared features of or aspects of deed methods. This is not a normative list. This is not something that's mandated by the deed specification. It doesn't say that deeds have to fall into one of these categories, but it's just some common tendencies that we are seeing. So in the beginning, we had deeds that are based on blockchains like Bitcoin or Ethereum. The idea was basically that if we want to have a decentralized identifier, then we need to register it in a decentralized system, right? So instead of registering deeds in the centralized hierarchical domain name system, instead of that, we register identifiers in a blockchain, in a DLT. So that was the first category, and it's still very much in use. By now, the second category here, where it says ledger middleware, that's similar. So those are types of deeds that still use blockchains, but they add an additional layer. So they add an additional storage mechanism that's cheaper and more efficient than a blockchain. Could be a distributed hash table or some classic replicated database, and the idea is you can write large numbers of deeds into that second layer storage mechanism, like a database. You can create or update 1,000 deeds in that second layer system, but you only need a single transaction written to the blockchain, and therefore to anchor those thousands of second layer transactions. That makes everything more scalable and efficient and cheaper. The third one here, peer deeds, that's especially interesting. Those are deeds that are not globally resolvable. So remember, we said all deeds have to be resolvable, but we didn't say that all deeds have to be globally resolvable. So there's also a class of deeds known as peer deeds that exist not on a global source of truth, or not on a blockchain that everyone can see, but they exist within the context of a relationship between two or more, between a limited number of participants, and those deeds are exchanged and maintained using certain protocols, agent protocols, and those are still valid deeds because they still fulfill all the core properties and provide the functionality that all deeds must provide, but they are just not registered on a blockchain. They're exchanged between participants of a relationship. The fourth one, static deeds, we saw that we began seeing those, I don't know, maybe about a year ago. Those are very, very simple, very constrained deeds that actually don't support all the basic functions. Those deeds can be created and resolved, but they cannot be updated and deactivated. Those are basically just simply public keys that are wrapped into the deed format. So you can do that. You could just generate a cryptographic key pair using any one of the cryptographic key algorithms, and you could consider the key, the public key, you could consider that also a type of deed because it is decentralized, it is persistent. You can construct a trivial deed document from it, and you cannot update it, you cannot deactivate it, but it's still aligned with the intentions of what deeds are for. So some people also call those identifiers cryptonyms or self-certifying identifiers, where the identifier is essentially the public key itself. And then final category that we've listed here, alternative deeds. So we see a lot of innovation and a lot of new ideas of what DIDs can look like, as long as there's a well-defined syntax that that fits in with the DID format, and as long as resolution and creation of the DIDs is sufficiently specified, you can create a DID method. So we see DID methods, for example, based on IPFS addresses, or DID methods based on Git commit hashes, and many other things. And those can also be DIDs. So that shows the flexibility really of how DIDs are a concept with certain guarantees and certain properties, and DIDs are not based on a single registry or a single protocol.
There you go. Thank you very much, Markus. That's a pretty exhaustive functional description of DIDs. And now we're going to go down the next level to the architectural reasons why DIDs work. And this part of the chapter was a lot of fun to work on, because after about 4 years of working on DIDs, and seeing how broad the concept had become, I personally was very interested in really diving down and going, what is the core innovation here? And this is another quote directly from the chapter that puts it this way. So what we posit is that what DIDs do is they really address a very core problem with PKI, public key infrastructure, that's been there from the outset. And it's not a problem with cryptography, right? With the math involved with public private keys or decryption and encryption. It's a problem with the infrastructure you need to actually make it useful on very broad scale and make it easy and safe for people and organizations to use. So in this section, we're going to actually walk through a slide presentation I created in order to build the narrative for this chapter, and all these diagrams appear in the chapter. This is just a much condensed version of explaining this, and this is the first time actually I prepared this, but only to write it in the book. I've only shown it to a couple people, so it's the first time it's been shown publicly. So let's just step through it here. All right, so we start out with the problem. The problem, again, is the very nature of how public and private keys work. And I call this the PKI Trust Triangle, because basically it doesn't matter what the algorithm is, what the cryptographic algorithm is behind it, whether it's RSA or elliptic curve or all the way up into quantum. There's fundamentally, it always comes down to there's a cryptographic binding between a private key and a public key. And they have those names because the whole point of the private key is that's what the controller controls in order to exert control and prove things on the basis of this relationship. And the other half must be shared. It doesn't necessarily have to be shared publicly with the world, but it's called a public key because it must be shared with whoever you wish to have to make a proof with, to have a secure relationship with. So this very basic trust triangle has a core problem spot. It's right there. It's how do you connect the controller with the public key? Specifically, how do you strongly bind it so that the relying parties know that they're dealing with that controller when they are, verifying a proof or decrypting a communication. Now, this half of that relationship is not the problem. The public key itself is just a string of bits. You either have it or you don't, and it either works or it doesn't. So that's not the problem. The problem is this other half of that relationship, the controller. And the problem is fundamentally, controllers are not digital entities. They're not a nice, convenient string of bits that you can just verify. They are these squishy things of people and organizations that need to be identified. So they need some kind of digital identifier to be captured in this milieu. And that means that the real PKI Trust Triangle looks like this. It's got this fourth element, and what we need to relate is the identifier, the private key, public key, all of them to the controller. Okay. So when you see this and you see, okay, it's actually these four things, you can see the problem actually has two parts. Part one is binding the digital identifier to the controller. That's the problem spot number one. And part two is you still have to strongly bind the identifier to the public key. That's that second part right there. So PKI has shown that both parts of this are hard. And we're now going to go through the solution that is PKI as we know, a conventional public key infrastructure. So the first part of the problem, how do we bind the digital identifier to the controller, regardless of what that controller is? How do we do that binding? Well, we need an identifier, but you know what? There is no existing identifier that works particularly well for this class. This table captures basically the options were available when X509 digital certs were being created, and they settled on basically these two. Either a URL or X500 distinguished name in the global directory system that is the X500. That should say X509 search down the corner. That's a typo there. So anyway, those were the two that were settled on, but neither one is perfect. But in any case, once we have that identifier, now how do you strongly bind to the public key? Well, in the context of public key cryptography, well, you do it with a digital signature, but the challenge is whose signature? If you just rely on the controller's signature, then the controller could bind their public key to an identifier they wanted. So who do you trust for that? Well, the answer under conventional PKI is a trusted third party. Someone who can be trusted to digitally sign that binding between the public key and the ID, and that's where we got the role of the certificate authority, or CAs as they're known. That's what they do. They come in and they create that red square there, which is the essence of a public key certificate, also called a digital certificate. And they sign it with their own private key, and others can verify that that identifier is really bound to that public key. So the challenge is there are a bunch of problems with the solution. So first of all, it does depend on people, and people are fallible. It adds cost and friction to every relationship where you need to verify, you need a verifiable public key. As we pointed out throughout this, it's centralized, and that stands for single point of failure, which is an issue with security and distributed systems. And lastly, of course, identifiers can change, and every time an identifier changes, you have to redo the whole thing and reissue new public key certificates, which actually keys can change, and you have to redo the public key certificate every time keys change as well. So all of these issues add up to, let's see if there's a better solution. So part three, we're going to talk about a different solution to PKI called self-certifying identifiers. I want to credit Dr. Sam Smith introduced me to that term. And it's really actually at its core a very, very simple idea. The approach is doing the binding entirely with cryptography. And it works like this. If you have a self-certifying identifier, you have the same trust triangle, only the identifier is actually generated from the public-private key process. Now, there are various ways this can work. Again, it's like DID methods. There's not one way to do it, but the bottom line is the identifier is generated on the basis of this, and the controller publishes it just like the controller publishes the public key. Now, if we look at this, it actually solves both of those core problems for which we invented PKI. First, the binding of the public key to the identifier. As long as you trust the math, it's as strong as the binding of the public key to the private key. And every DID method has to show that it's got a way of doing this, of showing that control over the public and private key pair equals control over the identifier. And then it solves the other problem because binding the identifier to the controller works the same way the private key does. The controller is the only one who can generate and publish that public key. So as long as they control that private key, they can prove control of that identifier. So we managed to solve both of those problems. The only part of the problem we haven't solved here is key rotation and recovery. And that's why the solution is using self-certified identifiers that are public keys This is the limitation they run into. Every time you rotate your key, you'd have to change your identifier. So what happens if you change your keys? Well, that leads us to the DID solution. So DIDs and DID documents can solve that key rotation problem for self-certifying identifiers. So stepping through, it's not complicated. First, the DID controller creates a key pair and the DID. So we're saying now the self-certifying identifier up here is a DID. It has all the properties that Markus has just finished talking through in detail. Now, that's public-private key pair number one. That's creates the original DID. Now, what the DID controller does is publish the original DID document containing those. That's what this looks like. If you look at a DID document, its essence from a PKI standpoint associates the DID as the identifier with that public key. And again, this is DID document number one. Now, we're going to rotate the keys, and when it happens, that means the DID controller publishes a new DID document, signs it with the original private key. And there you have it. It is now a new public key signed by the previous public key. So you have what is the equivalent of a digital certificate, only it's published directly by the controller. So it forms a chain of trust across all the DID documents, all the key rotations that may take place, that can be traced back to the original self-certifying identifier. Essentially, you've created digital certificates that are decentralized because they don't require any certificate authority or other trusted third party. They just need a way to get access to that chain of documents that go back to the original self-certifying identifier to verify it. And of course, blockchains and other mechanisms can be very, very handy for that, but they're not the only ones. All those different types of DID methods that Markus talked about, except for the static ones, can work for this. It doesn't require a blockchain. The pure DID method can do this just through a series of updates directly between two pairs. So it turns out, I'll finish up here with, there are two other nice benefits of this DID solution, okay? Neither of which is addressed by conventional PKI. The first one is, it actually provides a great way to identify something besides the DID subject. This is why I brought this up early in our presentation here. You can now turn around, and with this exact setup, you can turn around and say the controller creates the key pair, creates the DID, but uses it to identify something else. In this particular example, one of the most common things that comes up is, how do you establish a DID for a newborn? Newborn's obviously not in a position to be the controller, but the controller, presumably one of the parents or a guardian, is able to generate the DID identifying the newborn, publish that DID, and maintain this, and even do key rotations and everything else until that newborn is in a position to take over control of that. And it's actually pretty clear from this, how would it do that? At that point, the child, let's say they reach the age of maturity, they would generate their own key pair, talk to the controller as in, the guardian relationship, and say, here is the new public key that I want you to publish in a DID document. And when the controller does that, transfer of control has taken place over to that now grown young woman or young man. So again, this pattern now can be used for anything, any person, organization, thing, abstract concept, a data structure, whatever it is that might need to be identified by a DID. Every control in the world can identify and create a cryptographically provable identifier, a persistent identifier for whatever it is they want to identify. So that's the first one. Go ahead.
Just a small question, because I think it's good to bring it up now, maybe.
Yeah.
From Francis, he's asking, when you did the rotation example right now, if there's a problem with the previous private key, how would you sign a CA or a new pair of keys, or a new pair of key to form the previous one if you don't trust it anymore?
I love that question. It means someone's really paying close attention. I don't have a diagram for that, but the best answer that I've seen out there, and I've been at this a couple of years, is I call it the backup key approach. I actually spent a good hour talking with Dr. Sam Smith at the DID working group meeting about this last week. The approach is you actually at inception or very quickly, you create a cryptographic commitment to the next public-private key pair that you're going to be using, and you publish that. And you're basically protecting one or a string of other keys that you do not share, you do not expose unless there's been some kind of a compromise. And I think, you know, we started down that path in what's called DKMS Design and Architecture document. You can just Google that term DKMS Design and Architecture at Hyperledger and find the 70-page document we published on that. And we had the notion of that, but not the depth that Sam Smith has taken that with what's called KERI architecture, K-E-R-I. And just Google his name and KERI, and you'll get his papers on that. Sam's going to be collaborating with us on the decentralized key management portion of the book, and there'll be a lot more detail about how to do those cryptographic commitments to protect, basically forward-looking protection on your private keys. So it's a great question. Glad it came up. Are there any others in the queue, Alex?
Yeah, just two more. Like Francis is also asking, is this coming from the seed? And then Michelle, he's following up with another question. So if you lose that key, how do you recover that key?
So the answer is yes. This is coming from initial seed. And the second one, I actually plan to work with Sam to develop a series of diagrams like this that cover the cryptographic commitment approach to protecting those backup keys. So I'm not going to try and just walk through it right here. I think when when we do the probably multiple webinars on the decentralized key management portion of the book, we'll cover that. So I beg for a little patience on that one because it obviously gets fairly complex. These are the simplest diagrams. I was managing to get the main problem out. Any other questions in the queue?
No, that's it.
Okay. All right, so anyway, this is the first of the additional benefits. The other one is, oh yeah, I point out here, it's not just guardianship we talked about, but anything that needs to be controlled that's not a person. So directorship of organization, or what we call controllership of things, they all involve that same pattern. So the other benefit is discovering how to interact with the DID subject. So it's not just, in many cases, you don't just need to know the public key, you need to know where and how you can interact in a term that's broadly in SSI being called agents, or in some cases, if it's directly with the data involved with the subject, it might be a hub. But what you need is URL, what Markus referred to in a DID document as a service endpoint. And as you can see here, if you just include that in the DID document that is signed or otherwise verifiable as being controlled by DID control, then you know you've got an interaction point at which you can interact. And one thing I like to point out is, even if you don't trust the DID document itself, but you have the public key, you can challenge the DID controller and receive an authentication via whatever that service might be, to be sure that you're actually, dealing with the verifiable controller. So I think it's a very powerful pattern, and adds the whole discovery dimension to make this decentralized public key infrastructure interactive. And that's the end of that. We have just a couple slides left to go down to the semantic level, because we knew that we'd be going over time if we go deep into that. We have to hold back a little bit to entice you to read the chapter. But I think what I'll do is I'll go ahead and finish this, and then we'll take any of the questions we have. So when we go all the way down, we're looking at, so what do DIDs really mean? And that's a very broad question, both semantically and for the growth of the web. But one thing that we thought was fascinating was to put them in the context of the evolution of all types of addresses that we have been using. I've been meaning to put together a table like this for a while, and I just I just love doing it because it's fascinating to look at how we have evolved. And I'm not saying every address we've ever come up with is on this, but as a general progression. Markus, I know what was your reaction when you first saw this table?
I don't remember what my first reaction was. I don't know. The only thing, but what I said in the beginning is that we realized early on that we want to build SSI and we want to build a new self-sovereign identity system. We need to start with the identifiers because we need a way to refer to one another and to have addresses in order to do connections and relationships and anything at all. So that's why we need a new identifier and not just a new type of protocol, a new type of cryptography.
Yeah, it's this. One of the things that fascinated me was basically the increasing pace of new addresses that evolved as we evolved digital infrastructure, right? I mean, going from a telephone number to credit cards and fax numbers, and then things really started to speed up. But the other point we make in this section is to talk about the evolution of new address isn't because somebody needed a new way to necessarily identify something. It's because there's a new type of network that needs that address. And that's why we've listed each type of network we talked about here, or the capability that's needed on that network. Like the web needed both machine-friendly addresses for persistent connections like URNs and human-friendly addresses for URLs. So if you apply that question to DIDs, the real answer comes down to they enable the new kind of network they enable are trust networks. And it's where all the relationships can be trusted, not just specific, oh, I need to have a SSL certificate for my website so that people can trust buying something from me. In a DID network where all the actors, be they people, organizations, or things, are identified with DIDs, you can have trusted relationships of whatever dimension of trust you want everywhere. The entire thing is cryptographically trusted, but not necessarily just cryptographically. So the way we put it this way, the new type of communications network functionality here is DIDs enable both cryptographic trust and then human trust to be layered over that. And in the book, you know, and if you've listened to earlier webinars on SSI Meetup, you know that that's the mechanism we call the trust over IP stack. And it looks, you know, in its full, we'll do more webinars for other chapters and to talk about this in detail, but the technical half of the stack is here, the governance half of the stack is here, and you can see that DIDs are the very, very, you know, base layer. These public DID registries that we've been talking about, pairwise DIDs or static DIDs are used inherently at layer 2. Those enable the human trust triangle of verifiable credentials at layer 3, and then at layer 4, governance authorities and governance frameworks will have DIDs, and these different roles we show over here as this trust RP governance stack evolves. Every one of those roles will have the participant playing that role will have a DID, and they will have a verifiable credential that includes that DID that asserts their role in a particular governance framework. So you'll have a common way of describing, no matter what your governance framework is and what your trust network tackles, there's a common way to describe it, a common way to identify all the actors, a common way to establish cryptographic trust, and then layer on the human trust of verifiable credentials. So that's really, when it gets down to the semantic layer, what a DID is about is a way of establishing digital trust everywhere. And when we say everywhere, we mean everything that we deal with on the internet, everything on the web, and things that haven't been invented yet. And that's as far as we're going to go here. There's again a few more fine points in that section at the end, but I think we've used up our time here to acquaint you with the chapter. So questions?
Yeah, I mean, we have one comment, and I invite everyone to share the questions now. From Alan, he's saying you missed out GPS coordinates. That's in the page where you had email URL, etc. So he's suggesting to add that. Maybe we can update that.
It's a great suggestion. We forgot to mention that because the book is still in progress. Yeah, please, any suggestions, gladly we will add GPS coordinates. That's perfect.
Yeah, cool. Yeah, which is true. Actually, this chapter can be read online, and you can give feedback to the chapter. So if you get it online, then please give feedback, because that would be awesome. And then Francis is saying, thanks, I get it. It is what I thought, but there's still an issue with that for scaling and integrating that to full-size organization. Example, when you have employees from a government that can't produce verifiable data, we need to track this chain of keys. If possible, I would be interested in connecting with Drummond. So he's sharing his email here. I'll send it to you via Slack, Drummond.
That's
Maybe
great.
you want to comment.
Oh, well, I strongly agree. The mechanisms for decentralized key management when it comes to organizations and delegation is a wonderfully rich topic. I think we're still in the early days. And the underlying primitives that we've covered in that section, I think they all apply. But once the controller is no longer the I'll back up to that as we talk to it here. Once the controller is not, I'll go to this slide right here. Once the controller is not the subject, and what you're identifying is, for instance, organization, then the way you set up key management for that organization and for employees and operating units within that organization, and even smart contracts that they may be operating, that's the essence of what this new decentralized cryptographic infrastructure will look like. And as much as we might sort of have got down to the DNA of DIDs here, I don't want to pretend that we've got all the answers for how this will work. We're still at the earliest stages of actually establish this operational infrastructure.
I mean, on the private key side of things, I think there's a lot of innovation that has happened in the cryptocurrency space, and identity is of course something else, but there are probably some lessons to be learned in terms of wallet security and cold storage and air-gapped wallets and multi-sigs and some of these things that the cryptocurrency community had been working on when it comes to seeds and derived keys and all of that. I think a lot of these concepts will be could be valuable here as well.
Completely agree.
Yeah, absolutely. And actually, it's one of the things we want to encourage, because I think the connection between the cryptocurrency blockchain space and the SSI community is still not as strong as it should be. And I think there's a lot of overlap, especially when we talk about questions like DKMS and stuff like that. But in reality, also many other things for the decentralized economy they want to create. So if there are no other questions, Drummond, what I would suggest, if you can go to the last slide, I have one more question that just came up here two more questions came up. Okay, doesn't being decentralized semantically depend on a specific resolver method?
I'm not sure if it depends necessarily on a specific resolver. Well, there's the larger question. I sort of hear two questions there. Is any particular, when you say resolver method, I'm understanding DID method, because that's what specifies how it's resolved. DID methods themselves have different levels of decentralization. In our earlier webinar today, we talked about a deliverable of the W3C DID working group is a document called the Decentralization Rubric, which is a whole series of tests or methods of evaluating how decentralized a particular DID method may be according to your criteria of what's important. And it's a deep, broad topic, and I'm certain that there'll be hopefully a SSI meetup webinar on that topic once that deliverable is ready. So there's how decentralized is that method. And then there's the question of, with over 40 methods out there, how decentralized is the entire infrastructure? And I'm growing increasingly confident that the variety of DID methods out there and the variety of blockchains or distributed ledgers or distributed file systems and other back ends that they're being developed for, we're going to have a very, it's like decentralization squared. We're going to have a whole lot of options, and they'll be, competing in a good way, a survival of the fittest for what is most decentralized and, fit for purpose. And Markus, any thoughts on that?
Yeah, I agree. There are many different types of decentralization. Obviously, you can argue whether Bitcoin or Sovereign or Ethereum or any of these DID methods is in itself decentralized. That's what this decentralization rubric is for, to try to answer questions related to decentralization about specific DID methods. But then, as you said, the DID mechanism itself is a form of decentralization, because you should be able to replace one DID method with another, and since if they're all standards compliant, everything on top of that, the whole stack should still work. So you should have some choice there. And then there's decentralization of the resolver infrastructure. There's decentralization of agents and hubs and some of these higher level components. If we register, if we have the perfectly decentralized DID method, but then everybody is hosting their agent with a single provider, then again there's a weakness there. Then.
Great. Then Paolo, he's asking a popular question. So he's asking, the cryptographic mechanisms that are being considered, are they future-proof? Are they quantum-proof? What can you tell us about this?
It's a great question. It's a common question. In fact, it's coming up more and more, and I don't blame it. There was actually a good discussion of that, not in the main line, but in one of the breakouts during the DID working group meeting in Amsterdam last week. The short answer is, in that same vein that we talked about earlier in terms of how you'd structure the DID document and the keys you can put in there. One suggestion has been what people call the quantum emergency key, which is you're publishing even though it's not intended for use until the quantum emergency happens, that you do publish a key for which you keep the private key safe, that is quantum proof. And obviously it's big and long and will take up more storage space, but it's not intended for use until you get to that point, at which point you rotate over to using that. And then I've heard of a couple other approaches that are coming from experts far
Mm-hmm.
I'm not only not a cryptography expert, I'm nobody's quantum expert. It is, but it's very actively being discussed, because I think it's as big an issue for decentralized PKI as it is for centralized PKI, because the attack surface is every place you have a DID document. But that's all I can say on that. Markus, do you have anything you want to add to that?
I'm definitely not an expert on that. The only thing that comes to mind is that the DID document concept is extensible, right? So just because the current public key algorithms that are being used, if they are not secure anymore, then others can be added, and that the document can be extended, actually, not just to support different key types in the future, but to support different so-called verification mechanisms, right? So strictly speaking, in a DID document, public keys are just a type of verification mechanism, how the controller can prove that they control a certain DID, but even that is extensible. So perhaps in the future there will be verification mechanisms, ways to prove control that are not even key-based, right, or traditional, based on traditional asymmetric cryptography. So yeah, we'd have to work on that and see what is secure and what is not, but we will not have to reinvent DIDs themselves, right?
And we talked on this morning's webinar, which about a key mechanism that the DID working group has or agreed on last week, which is a registry of extensions that will be specified in the DID core spec and most likely run by W3C as they move into starting to host registries for different specifications. And the nice thing about that is it's a widely shareable mechanism for publishing extensions, such as new cryptographic algorithms or verification methods, as Markus said. So as good solutions are developed for quantum proofing your DID documents, they can be registered there, and it just makes it that much easier for them to spread throughout DID infrastructure, and you know, get the best of as Markus said, we can't design all future proofing in there, but we've designed it to be extensible so that it can continue to evolve.
Excellent. Yeah, I mean, I would just add to that. I mean, like in the Bitcoin crypto space, it has been an argument for a very long time that what happens when quantum cryptography comes up and quantum computers and everything. And I think, like, I mean, obviously for identity, it's much more important than for cryptocurrency, because I mean, if people can steal your identity, that's a big deal. But at the same time, like as quantum computing emerges, just quantum cryptography emerging, and there will be changes being made. And I think as Drummond and Markus highlighted, it is being made extensible so that these networks can be adapted to those changes. I think there are no other questions. So as we said, this is just an insider presentation about what is upcoming in this chapter about DIDs. We will be doing many more about like these in the other chapters that we'll be working on, that will be published this summer. You can read this chapter already right now. We would be really happy about any feedback on this as the GPS recommendation that was just made right now. And yeah, please have a look. The upcoming webinars we have are 25th of February, we have Tim Bauer, who will be talking about money and identity. Then we have eSatus, which is a startup in the SSI space from Germany, on the 27th. On the 28th, we have John Phillips from Australia, who will be sharing a very nice method about how to explain to people that don't know anything about SSI, about how SSI works and why it's important. And this is the stuff we have upcoming. Many other things also coming up for March and April. If you want to join any of these, please join our Telegram channel. You have it on the website of ssimeetup.org. You can, on the footer, on the bottom right, you can see the links to Twitter, Telegram, Facebook, LinkedIn, and all those channels where we distribute and inform everyone. And you can, of course, also sign up to the newsletter where we send out an email every time there's a new upcoming webinar. Thank you so much, Drummond and Markus, for making time and sharing all this with us. First in the DID working group webinar we did a couple of hours ago, and now for this. Any final thoughts that you would like to share?
Not from my part. It's I feel DIDed out for the day. I hope. I just think it's we've got as deep into the content and as current as in the earlier one as we can. So I look forward to feedback and helping it improve the chapter, and then doing many more of these. I think they're literally going to be, 24 chapters that are worthy of SSI Meetup webinars. So thank you, Alex.
Yeah, thank you from my side as well. I don't have much to add. Just been really nice to be part of this and to be contributing to this very important book. I think it's great that this is happening. Yeah, wonderful. We also people are saying thank you here in the
questions channel. So Michelle, thank you. They're saying great job for Michelle. Big thanks to Drummond and Markus from Fabian. And then Nabil, he's finally asking, can you please add a chapter for using DIDs in IoT? I mean, maybe you want to comment on that, Markus and Drummond, but just to say to you that we have a specific chapter. We will talk about the use cases of IoT and SSI. And maybe Drummond, you want to add anything else, or Markus?
I think that chapter will definitely go, deep into how DoDs will be used with SSI. And I'll point folks, I believe it's in the first 10 webinars, the one you did with Myrnal from why is it running off my head? But he did a wonderful webinar with you, Alex, on DIDs and IoT.
Yeah, I'm just searching for that. Just give me one sec.
Yeah. Occam is the name of the company.
Yeah, exactly. Occam, yeah.
Yeah. So definitely check out that webinar. He gave a great sort of tutorial on his thinking about DIDs for IoT.
Yeah, if you search for IoT SSI meetup, Occam or Mrinal, that's his name, you can check out the video and the recording we did at the time for that. Yeah, great. I think we covered all the questions, all the comments. Thank you so much, Markus. Thank you so much, Drummond. Thank you everyone who joined us today. Please check out our Telegram channel and all the other social media channels. Check out the book if you have time and interest. That would be great. We look forward to any feedback, and we will be doing many more of these, and for what we hope will be like a really high level but also deep level introduction book to the big world of SSI that will be really, hopefully, I think, reshaping the internet. Thank you so much, everyone.
Thank you.